Precipitation reactions. There are three main types of aqueous reactions, or reactions that take place in aqueous environments where it's dissolved in solution. One of them is precipitation, another one's acid-base, and then the third one is redox. So in future topics of Unit 4, we'll be covering acid-base and redox in detail. This one's going to focus mainly, the rest of the notes will focus mainly on precipitation reactions. Soluble versus insoluble. Got to know and be able to read those solubility rules and know, of course, a certain amount of them, because you have to be able to decide whether it's going to be soluble or insoluble. The ones that are soluble, will stay dissolved in solution. You won't be able to see them. And we use the AQ next to it. Okay, that symbol is what's written in the equation. And the insoluble ones that don't dissolve or will precipitate out when combined, those ones will have an S next to them in the equation here. So the picture is pretty much the same concept as the animation. Has the silver nitrate, which is soluble because it has AQ next to it. The potassium chloride, which is AQ. You take those two, you combine them. The potassium nitrate stays soluble, but the silver chloride precipitates out and it forms a white powder at the bottom, as seen in the animation. This is another example, also showing the particulate model diagram too, to help you start to get to know these a little bit better. This is barium nitrate and potassium chromate. The overall regular reaction, stoichiometric reaction, is above in red here. And what you'll see here is, this is like initially combined, the initial, before any reaction takes place, the initial dumping. And what you see here is your bariums, okay, these ones, and the chromates, which you can tell also because they have 5 atoms linked together, or 5 little circles linked together in the picture. Those ones form an ionic bond and start building a lattice crystal at the bottom. And that's why you see the powder fall to the bottom. The potassium and the nitrate, they stay dissolved in the water. So they're still floating around. They aren't really participating in the reaction. And we're going to define this in a little bit, but they're called spectator ions because they watch the reaction, but they don't actually participate. But here showing you that the barium chromate is a light yellow precipitate falling to the bottom like so. So that brings us to the solubility rules. Now, you don't really have to memorize everything on here, but you definitely want to have these out when you're doing your problem set, because the ones in the textbook use all of the different stuff. So you want to be able to reference it. Now, what I typically tell students to memorize or know are the first two, and that's why I bolded them, 1 and 2, because if you know 1 and 2, pretty much you can figure out the rest. Alkaline metal salts are always soluble, so group 1, lithium, sodium, potassium, rubidium, cesium, those ones, always soluble. So if you ever see that in a compound, automatically, going to dissolve. Ammonium, one of the polyatomic ions. This is ammonium. You do have to know ammonium. It is on the polyatomic ion sheet. That is one that they say that you have to know for AP specifically. Ammonium salts are always soluble too. So if you see NH4 in it, always soluble. Those pretty much covering like the cation side of things. The ones that are positively charged. Those ions that are positively charged. For the anions, we're looking at nitrate. That one's important. Given. And you probably should have like the nitrate formula memorized, NO3 - 1. I'll circle a few, like these are the ones that you should definitely just like know off the top of your head. Other ones you should be able to figure out from the formulas. This is chlorate, perchlorate, and acetate. Now, the way that we wrote acetate last year, we wrote it like this. But the way that AP likes to write it is in the organic form. This is the organic form, where they put it so that it looks, you know, the way that the atoms are arranged, like those H's are on the first C. Then you have the C double bonded to an O with another O on the end there. So they write it kind of like how the atoms would be bonded together in the ion. Acetate is organic acid. It's acetic acid when it has the H on there, which is better known as vinegar. So that one's one that pops up quite frequently. So if you basically know that both of 1 and 2 are always soluble, then you'll be able to figure out, you know, which ones are insoluble. There are notable exceptions to different ones here, especially for the chlorides, bromides, iodides group. It's usually silver, mercury, lead. They don't usually give you mercury stuff. It's usually lead or silver that you would see in a problem. And then, of course, sulfates have lots of exceptions. Okay, includes the silver, mercury, lead, but also the barium, strontium, calcium, which are the heavy metals in the alkaline earth group 2. Pretty much everything else are going to be insoluble. They don't really do a whole lot of fluoride compounds, so I wouldn't really worry about number 4 that much. But like I said, when you're doing the textbook problems, have this out, because who knows what randomly one's going to generate for you in the problem set. Now, according to AP, although last year was kind of a little bit of a glitch in the free response for this, they say you're only supposed to know sodium, nitrate, ammonium, and potassium, SNAP. You're supposed to know those 4 are always soluble. However, they did ask a perchlorate thing at the end, and a lot of people got confused about that, and I found that to be, you know, kind of in a little bit of a gray area. That's why I would tell you to know 1 and 2. All right. This is according to AP. But like I said, last year's free response, they had perchlorate in there. A lot of people thought the silver perchlorate was going to precipitate out, because silver is obviously an exception to many rules up here. So it was a tad bit confusing. So I'm just going to note that. All right, so now we're going to practice using our solubility rules. See if we can figure this out. So take a moment to look at the solubility rules. Okay, so which of the following ions form compounds with lead 2 that are generally soluble in water? So you look at your solubility rules. What about sulfides? S-2. Nope. Sulfides are typically insoluble except for with alkali metals and ammonium. How about chloride?
Nope.
Nope. According to our exception rule, chlorides are generally soluble except for silver, mercury, lead. So that's out. What about nitrate?
Yep.
Nitrate's always soluble, so definitely check that one. How about sulfate?
Nope.
Once again, has notable exceptions, and lead is one of them. Now what about E? What do we make of E? Is E going to form a compound with lead 2?
Yeah.
Do cations form compounds with other cations?
No.
Oh.
No, why? Because what do cations do to other cations?
Repel.
Repel, positives repel. So
That was a trick.
that was sort of a trick, yes, exactly.
Yeah.
It's not going to, cations won't form compounds with other cations. In an ionic compound, remember, you always have a cation and an anion. The positive and negative has to attract. Yes, question?
So would the lead show us precipitate for all these soluble, like nitrate example is soluble, but lead nitrate or whatever it's called, would the lead just precipitate while the nitrate stays?
If we combined it with something else, like if we had lead nitrate in one beaker and we had potassium chloride in another, we dumped them together, well then the lead chloride would precipitate out.
So, but it together the compound would be soluble.
Would be dissolved in the water, yes. And the only way to get that compound back would be to evaporate out the water, to heat out the water.
Okay.
Yeah. Okay? So the only one there that makes sense, nitrate. All right, now we're gonna practice thinking of the double replacement reactions here and seeing if we can find a precipitate combination between the two. So when you're looking at these, I'm going to work A for you, and then you can try B and C on your own. You're taking two ionic compounds. Remember, ionic compounds consist of like a metal and non-metal combination usually, or you'll see the notable polyatomic ions in there. So potassium's a metal, nitrate is one of those polyatomic ions, but also consisting of non-metals. Remember on the periodic table, to denote metals between non-metals, look at the staircase. Everything left of the staircase is the metals, to the right of the staircase are the non-metals, and there's like 6 of them on the staircase that are considered to be the metalloids, the ones that are in between. All right, so doing, taking these, we have compound plus compound. So this is going to fall under the umbrella of double replacement or double displacement. That means the cation of one should combine with the anion of the other. So potassium would be the cation, the chloride would be the anion that would combine. Now, when you're looking at this is where formula writing becomes an issue. If you remember back to your formula writing days of how we come up with the formulas for ionic compounds, is always based off of the charges. So the ratios form because the charges must add up to 0, must be a neutral compound. But that means we have to remember what their charges are, and we have to figure that out. Now I put some charts in the back of your notes, attached them to the back of your notes that you're welcome to use to get more familiar. The polyatomic charts, there's one that also has common cations and common anions off the periodic table, as well as the polyatomics. Now, so this simply means that you have to remember, like group 1, the alkaline metals. They have how many valence electrons? They have 1, so their oxidation state is always +1. So as they lose that 1 electron, they go to +1, okay? Alkaline earth metals, what's that? +2. The transition metals, most of them in the transition section are going to be multiple oxidation metals. What does that mean? They have more than one possible charge. Except for the important ones that you have to know for AP that are in the transition section that do not have more than one charge. Well, here we need to know silver and zinc. They are on the list. Silver is always +1. Zinc is always +2. And yes, I know in Honors Chem 1 we always talked about cadmium too, but you won't see cadmium all that often in AP. So, but zinc and silver, okay, are ones that you have to know. And I have a little way that you can, use to help memorize that. Because group 13, the barium group, the metals in that group form what kind of oxidation state? What charge? +3, right? So barium, not barium, boron, the boron group, like aluminum, gallium, the metals in there go to +3 usually, okay? Now, a way to remember the zinc and the silver off the periodic table, if you look at aluminum, here's aluminum, here goes zinc, right? They're in a diagonal. Everybody following me? We know this group is +3, or I guess technically we would say 3+ if we're writing it as a formal charge. In the diagonal, going down, this is 2+, this is plus. So there's +3, +2, +1. That's an easy way to remember them. Okay? For these ones that are kind of exceptions to the general rule. Now, for the rest of the transition metals, they'll do one of two things for you in the problem. they will write the name of the formula in there. They'll say it's like iron 3 phosphate. So you know it has Roman numeral 3 in there, you know that that iron is +3. They will give you those context clues that you're supposed to use to figure out the charges. Or they'll give you, you know, something that you should know the charge of. Like if it's iron 3 nitrate, well, you know nitrate's -1. You should be able to figure out what the charge is on the iron, just working backwards from the formula. So those are some kind of things, and yes, we're gonna have to refresh a little bit and do some practice here. But use those at the end of the notes to help you, especially when you're doing your problem set. So that brings me back to A. Sorry, I diverged there. We have potassium that's going to combine with the chloride here. So what's potassium's charge? +1, because this one, or 1, or just plus, it's an alkali metal, so it's in group 1. Chloride is a halogen. So on that side of the table, group 17, what is its common oxidation state in ionic compounds? -1. Halogens go to -1, so this is going to be -1. I guess we do +1, -1. All right, so if those two are going to combine together to form a compound, we need to add it up to 0, so how many of each do we need? 1 of each, right? So this is going to form KCl. Now we have to combine the other two together. The nitrate would combine with the barium here. What is nitrate's charge? -1. And what would barium's charge be? +2, because it is in the alkaline earth metals, group 2. So, if we're combining this, how many of each do we need to write the formula? We need 2 of the nitrates to balance out the 1 barium, because the charges have to add up to 0. So this one would be Ba, and then you use the parentheses, you gotta keep the group together and stick the 2 outside. It's all coming back to you now? All right. Now that we know our products, our possible products, so here are our 2 possible products, then we go to our solubility rules, and we look at them. So we look at the rule for the chlorides, and the rule for the potassium. So is that soluble or insoluble?
Soluble.
Soluble, so this would be AQ. How about the barium nitrate? Nitrate's always soluble. This one here, AQ as well. Now, if everything's AQ, that means nothing reacted. Everything's just dissolved, floating around the water, not doing anything. So, for this one, you would write no reaction. And we abbreviate reaction RXN. Nice little thing to do there. So if everything stays AQ, that means no reaction has occurred and you just have a bunch of ions floating around in the water. Question?
Is it okay to leave out that 1 chlorine that was originally in there?
Well, no, we would, if we were writing out the full equation, we would balance it using coefficients.
Okay.
So you're not really leaving out the chlorine, but here we're not really balancing, we're just looking for anything precipitating.
Oh, okay.
Yes, question?
Is it for the product side, if they're both AQ, does that mean no reaction, or does the reaction side want to be all AQ as well?
Well, basically, if everything's dissolved, you know, on the product side, if everything stays AQ, like you could start out with a solid, you could be dumping a solid into a solution that's AQ on the reactant side, but if everything stays dissolved, no reaction has occurred.
But it's just the product side.
So really, it's the product side. If everything stays AQ, you know no reaction occurred. Question?
Where does the 2 go again? It's from the CO2. You just not.
Well, once again, if we were writing out the entire equation, we would balance it using coefficients. So, but here, we're not really writing out the full equation. We're just looking for something to precipitate.
So if you were balancing out, would you just use 2 KCl?
If I was balancing it, it would be like this. So yes, obviously we wouldn't leave it like this because it looks like we have what? Destroyed a chlorine and created a nitrate. Okay, we're not gonna do that. So yes, we would put that there, and we put that there. So, but right now we're not really concerned that we're balancing it. We're just looking for, in our possible products, are either one of them going to be a precipitate?
Thank you.
Okay? So go ahead and try B and C. See if you can figure them out. Just look for the products. You don't have to write out the balanced equation, but try to figure out what the products would be and decide if we have a precipitate. All right, so sodium goes with nitrate here. Hopefully you got that this is going to be NaNO3, right? Sodium's +1, nitrate's -1, so it's a 1-to-1 ratio. That would be that formula. And the other one, the lead goes with the sulfate, and we know lead's a notable exception. Lead, silver, mercury. So this one would be PbSO4. The sulfate's -2, the lead is +2, and if you didn't know that, you could have figured it out because there are 2 nitrates in there, and we know nitrate's -1. Yes?
Are the charges of the ionic compounds just something you memorize?
Yes, and most of them, you get them from the periodic table, because like the groups have a designated charge. Some of them are straight, like yes, you just have to know them, like silver's +1, zinc's +2, because those ones are just exceptions and they don't follow a group trend. But also, like I said, in the back of your notes packet, there is that listing where it does like group 1 is +1, group 2, it kind of tells you those. So if you get more familiar and remember those patterns, you'll be able to figure it out.
Okay, thank you.
But yes, so some of it's memorization, some of it's patterns off the periodic table. Now, looking at these, you got the double whammy, the alkali metal and the nitrate. So this is definitely what? Aqueous, very good. Lead sulfate though? Solid. So this one's going to be the one that precipitates. Okay? Now I'm going to erase this here so that we have room for our potassium hydroxide with our iron 3 nitrate. Now, K, of course, goes with nitrate, KNO3. Potassium's +1, alkali metal again, nitrate's -1. So that's a 1-to-1 combo. And we know that alkali metals and nitrates are always soluble, so that one's AQ. The other one, though, the iron, is going to combine with the hydroxide. So you might have had to look up hydroxide's charge. What's hydroxide's charge? -1. That one is definitely one you're going to want to circle and know, because hydroxide is all over the place in AP because it is also a base. All right, now iron here. Iron is in the transition metal section, the D block. You might have not known what the charge is because it has 2 possible ones. The iron can go to +2 and +3. But you could look here at the nitrate. There's 3 nitrates. So 3 -1s means the iron has to carry a +3 charge here. So when we combine the -1 with the +3, how many hydroxides do we need? We need 3. Now, if we look at our solubility rules, what does it tell us about hydroxides? They're insoluble except for when they're with alkali metals or ammonia. So, this one is our solid. This is the one that's going to precipitate. All right. Now, 3 types of equations here. And you're going to have to do these in the problem set, and I'm going to already straight up tell you that you're going to have one of these on the quiz, where you have to balance the molecular, you'll write out the complete ionic, and you will also do the net ionic from it. So, the molecular or formula equation is what you would think of as the regular balanced equation. The ones that we've been doing in Chem 1, the regular balanced equation, that falls under this umbrella here. And that also tells you the stoichiometric relationship, the mole ratios and other things like that. Don't worry, we're going to review stoichiometry for those that might be like, oh, I haven't done that in a while. But for now, we're just going to be looking at the equation. So here, for example, the reactants and products generally shown as compounds, so they're together as compounds. They always are going to have their state symbols next to them. And you would look for solubility rules to determine which ones are solids and which ones are aqueous here. So, for example, the silver nitrate plus the sodium chloride gives you silver chloride. We know that one precipitates out, and our sodium nitrate. This one's an easy one because it's all 1 to 1 to 1. The silver's +1, the nitrate's -1, the sodium's +1, the chloride's -1. So everything ends up being 1 to 1 here. So that's a really easy example. Now, they don't always, because, you know, some equations have balancing and have coefficients. Now, complete ionic or overall ionic equations, this is what they look like. They represent the strong electrolytes, the ones that separate and become ions in solution. The ions get surrounded by the water, okay? And they have charges on them. So that gives them the ability to conduct electricity through the solution. So anything with ions that are dissolved would be considered in the strong electrolyte category. And if you put the light bulb in there, it would light up the light bulb with the electricity. Probably remember that also from Chem 1. Now, for complete ionic though, that means you have to separate everything that is aqueous, everything that is in ion form in the solution. So if it has AQ next to it, you know it's dissolved in the water, so it needs to be separated into its ions. This is also where the formula writing becomes important because you need to be able to write them in their ionic form. So, in the previous one, we had the silver nitrate together like so, and it said AQ. So basically what you do is you just separate them into their ions. Silver's +1, nitrate's -1, so you write the formula charge to represent the ion. That's how you would write it. We also know that sodium chloride, of course, is aqueous. So we break that up into Na+, Cl-. The only thing that you would keep together here happens to be the one that is a solid. So solid, liquid, gases, and reactions, you would never separate them because they are in a pure form. But if it's aqueous, we know it's dissolved in water, it's a mixture, it's a solution. So yes, you would separate them into their ion form. All right, so the complete ionic ones are actually the ones that are long and you have to write out all the stuff and it becomes cumbersome. I'm going to tell you that. Now, the net ionic is shorter. Net ionic equations represent only the chemical species that actually react in the reaction, actually form a bond of some sort. So here, the silver and the chloride, those opposite charges attract, form the ionic bond, and we see the powder fall to the bottom. So we get our new substance, our new solid here. That ionic bond is stronger than the forces of water, so that's why it forms the ionic bond and falls down. So the ones that are insoluble basically have stronger forces than water, and that's why they do not dissolve. We'll go into that a little bit more detail, but that's the basic gist of it. So basically, we only write the silver, the chloride, and the silver chloride. The sodium and the nitrate that was in the previous one, where we saw them as ions on both sides, we call those spectators. They are watching the show, they watch the reaction, but they're not actually participating. So the sports analogy kind of holds. You're watching, some kind of sports event game, the ones on the field playing, those are the ones doing the reaction. The ones sitting in the stands watching the show are the spectators. They're not participating. So you basically cancel out your spectators and you only put the ones that are actually reacting. Now I put this in here, the flow chart for naming. If anybody doesn't remember naming, because like I said, in the problems, what they'll do is they'll usually write out the name for you. And then they put either in parentheses or next to it the formula for you. So they give you context clues in the naming. Don't forget, basically mostly looking at the left here for the ionic, a little bit maybe to the right for the acid naming. But if it is a mom, it's going to have a Roman numeral. And that Roman numeral does designate to you what the charge is on that multiple oxidation metal. Okay? We'll get more into like the covalent stuff, because those ones use the prefix names like carbon dioxide, carbon monoxide, those kind of ones. Over here at the acids, not sure everybody remembers the acid naming system, but we have 3 possible combinations here where you have the ones without oxygen. That's the hydro something ic. And you know, you can use the my ride has hydraulics. We used the little phrases last year that are helpful. The 2 others that have oxygen in them are the ones that have the polyatomics that end in -ate, the polyatomics that end in -ite. So if you look at your polyatomic chart, you'll notice that most of them end in -ate or -ite. The ones that end in -ate, they just do the root name with ic. So we say I ate something icky. So you remember that -ate goes with ic. And the ones that end in -ite, Sprite is delicious because the -ite turns to OUS. So can use those as a helpful way of remembering how to name the acids, because you'll see them, they'll write the name out, then they put the formula next to it, so you can go back and remember, you know, what you're dealing with here. Ionic compounds contain a metal, non-metal, or polyatomic ions. Molecular compounds contain all non-metals, so you might want to have that mental note there. So we look at the ones that are molecular or covalently bonded, and then the acids will have the H in the front. This is one that I incorporated into your notes packet as a good reference list. Like I said, it gives you the simple cations, the polyatomic cations over here on the left. Selected transition metals, that's not all of them, but like I said, you see the Roman numerals there that will designate the charge on the particular one. So if you see a Roman numeral, you know what the charge is for the name. The simple anions, group 17, 16, 15, and 14. So 17 is the halogens, 16 is the oxygen group, 15 is the nitrogen group, -1, -2, -3. Group 14 is the carbon group. Occasionally form an ionic compound, but most of the ones in the carbon group do covalent bonding or sharing of electrons. So you won't see too frequently the group 14 being used. Then the polyatomic ions over here. That's one list of them. I also gave you my list that I give Chem 1, which is this one right here, and ultimate ones that you really should know. Ultimately, of course, are ammonium, nitrate, hydroxide, chlorate, acetate, carbonate, sulfate, and phosphate. It's usually the 8 ones that matter, and remember that acetate, you'll most likely see it written in the organic form like so. They might use something else on here, but once again, they'll give you context clues so you can figure out the charges on the polyatomic from being paired with something on the periodic table or with something with a Roman numeral. So I would just make sure that you highlight these and get really familiar with those. These are the ones that most frequently pop up. And it's, you know, the AP exam is timed, so the faster you can go, the better it is. Alrighty. Now we're going to get into writing the molecular or formula equations, the complete ionic, and net ionic. So I'm going to do this example with you, and then I'm going to let you practice. And I believe there is one of the questions at the end of the problem set that has like 4 points because they give you like, I don't know, like A through D on that. And it's going to be time consuming, but it's good practice. So write the correct molecular equation, complete ionic, net ionic equation for the reaction between cobalt-2 chloride and sodium hydroxide. Now, making the assumption that you know that these are solutions. These are aqueous. Like so. All right. So, formula equation. We're starting here with our reactants. Like I said, it's making the assumption that these are, since we're talking about precipitation reactions, these are already in solution, ready to be dumped together. 2 separate beakers being dumped together. Now, we have to predict the products. write the correct formula, and then balance. So, here, the cobalt ion, the cobalt cation, is going to combine with what? OH, good. And what is the charge on our cobalt ion? It's +2, like I said, context clue here, Roman numeral 2. But you could also look at chloride. Chloride's a halogen. Halogens go to -1, so you could figure it out that way as well. So, this is +2. What is hydroxide? -1. So, when we write the product over here, how many of each do we need?
Just one.
One cobalt and two hydroxides. Okay? So you write out the product. Let's write out the other one, and then we will look for solubility rules and balancing. So that means that the chloride goes with what? Na. And we know chloride's -1. The charge on Na is what? +1. So our other product is NaCl. Good. Simple enough. Now for our products, let's look for solubility rules. NaCl, I'm pretty sure everybody knows that's going to be AQ. Just think of the ocean, has lots of dissolved salt in there. Now, the cobalt hydroxide. That one's going to be solid. Hydroxides are typically insoluble, except for when it's with alkali metals and ammonium. So now that we have that, we're almost done. Last step is to balance. What's out of balance?
Na chlorine.
Chlorine and what's the other one? Hydroxide. So let's fix. What do we put there? 2. And what do we put here?
2.
That fixes our sodiums, our chlorines, and our hydroxides. Very good. All right, so step 1, getting the molecular formula equation down. Now we got to do complete ionic. This is where it gets the long part. That's why there'll only be one on the quiz. We won't go further than that. And luckily, I think for these, they put them in the multiple choice section, so you just pick out the right one. You don't have to actually write the whole thing out. So, anything that's AQ, we got to separate. But this one is not all 1 to 1 to 1, right? We've got a couple coefficients of 2. We've got some formulas that have 2 in them, the little subscripts 2. So let's think about this. This is going to separate our cobalt to chloride here. So we know this is going to be CO2+, which is AQ. But every time this formula unit, which is the technical name for an ionic compound, the formula unit, every time one of those breaks apart, you're going to get one cobalt-2 ion, and you're going to get how many chlorides? You're going to get 2 chlorides. So we have to represent that here by doing coefficient of 2 in front of the chlorides. So every time that one breaks apart, we get 1 cobalt, and then the 2 chlorides, they get surrounded by water. So that's that part. Now we got to break up the other one. And for balancing purposes, how many sodiums and hydroxides do we need to make this work?
2.
We need 2, so we still have to represent that in there as well. So 2 sodiums and 2 hydroxides. Okay, so those are the reactants. And I'm probably gonna have to kind of do a little down here because I'm running out of board space. But for our products over here, the cobalt hydroxide is solid. We know it precipitates. That one we get to keep together. That's nice. So we're going to keep that one together. Now, over here, the sodium chloride, it's going to do what? It's going to break apart. So we get 2 sodiums and 2 chlorides. Same idea here. We need 2 to make the reaction work because of the balancing, because of the coefficient. So we also have to include that in here. Now we look. Which ones are reacting? Which ones are spectators?
The cobalt
Hydroxide is reacting.
So the cobalt and the hydroxide are reacting. That means the chlorides and the sodiums,
Spectators.
these ones are your spectators. So the spectators, yes. We don't write the spectators in the net ionic. We only include what's actually forming a bond. So for our net ionic, the cobalt 2 plus the 2 hydroxides, that's going to give us the solid. Like so. Now there's 2 other examples here. I want you to try to work out. Like so. Well, there's the answer again if you need it in the PowerPoint. But here are 2 other ones I want you to try to work. Give you about 5 minutes or so. Set it up. And we'll take a look. Okay, first one probably wasn't that awful because everything was 1-to-1. Silver nitrate, potassium chloride. Notice that the silver chloride precipitates out if you follow your solubility rules. And you end up with the potassium nitrate over there on the right aqueous. Break it up all into their ions here. Everything that's aqueous is going to be dissolved in there. And you'll notice, obviously, that the potassium and the nitrates end up being the spectators. So they cancel out. You know, they would go boom, boom. And then you're left with your silver, your chloride, and your silver chloride precipitate. That one was, like I said, on the easier side because the balancing is much easier. The next one, though, here, probably noticed that you had to balance the overall. And that balancing and write the formulas correctly had to be brought down into the complete and net ionic. So you needed 3 of the potassium hydroxides. 1 of the iron 3 nitrates gave you iron 3 hydroxide, which is the one that precipitated out here. And then over here to the right, the potassium nitrate stayed aqueous. Just remember to bring down the coefficients like so. And if it's a subscript, remember that when this breaks apart, you get 1 iron, you get 3 nitrates. So that's why you have to put the 3 there for the nitrates. Time that breaks apart, 1 iron, 3 nitrates. The iron 3 hydroxide stays together, and the other 2 stay broken apart because they're still dissolved. So these are your spectators. They're the ones that you would take out to write your overall net ionic equation here. You have the 1 iron, the 3 hydroxides. There you go. Now, this one is a little bit different. I'm going to walk you through it because this one has to do with a single replacement. Although it still kind of follows the same rules as what we were doing before in writing out complete and net ionic. The only difference is we have an element plus a compound, giving us an element plus a compound. So here it says when zinc metal is added to hydrochloric acid, the rapid production of hydrogen gas occurs. Showing in the picture too, right here. So we take zinc metal. If it's zinc metal, what phase is it in? It's a solid, good. Just write that in there. Plus hydrochloric acid. And acids by definition are automatically in water. Well, they're in water, so acids are dissolved in water. They have to produce hydrogen ions in water. So this would all acids you would always denote as AQ. Now how much acid has been dissolved in the water is when you get the higher concentrations. Like if more acids in there, it's higher concentration. If less acids in there, lower concentration. So those are our two reactants. It tells us that hydrogen gas is produced. Hydrogen gas is produced, H2, elemental hydrogen. Remember, this is an element plus a compound, giving you an element plus a compound. And remember, hydrogen is diatomic, so you would have to write in H2. Now, we have to figure out the other product for balancing. So that means which ones are combining here. The zinc and the chloride combine. And what is the charge always on zinc? +2, and chloride is -1, so this is going to be ZnCl2. And if you look at your solubility rules, chlorides are typically soluble, except for if it's silver, mercury, lead. Obviously, zinc is not one of those, so it is soluble. It is AQ. Now, overall ionic is the same thing as complete ionic, so we're going to go ahead and separate the AQs, the ones that are dissolved. Write that out. So solid stays there, gas stays there. You don't do anything with those because those are not dissolved. But here we're going to get, oh wait, sorry. Let's start back over. What did I forget to do? You need to balance it. Okay. What's out of balance? Good. Now are we balanced? All right. Now we can do complete ionic. Thank you. All right. So we have zinc solid here. And we have 2 hydrogens. And since we know chloride's -1, what is the charge on the H for the acid? +1. And H acids are always +1. Okay? So we have 2 H pluses and 2 chlorides. Over here, we still get our hydrogen gas. That does not change. And now we have our zinc chloride. We have to separate that. So this is Zn2 plus. And 2 of our chlorides form. Now what you'll notice in a single replacement, this is a single replacement, element, compound. There's only going to be one spectator. What's the one spectator? Where it is ion on both sides. Ion on both sides is going to be?
Oh Lord.
Because if you look, the hydrogen's an ion on the reactants, but it is an element which has 0 charge on the products. The zinc starts out as a solid, so it's not an ion, and it becomes an ion in solution. So those are not spectators. The only ones that can be spectators are their AQ on both sides. They are dissolved ions on both sides. So our spectator here is chloride. Now, we're going to take out our spectators and write out our net ionic. So, we do that, we should get zinc solid plus our 2 hydrogens. That's going to give us our hydrogen gas and our zinc ion, like so. And I know that looks a little bit different, kind of setting us for future lesson coming up on redox, but this is the redox form of the single replacement. Single replacements are always redox reactions. Now, if you don't remember redox, just a little preview here. What is the oxidation state of all elements? Any of you remember the oxidation state of any element? It is 0, thank you. So that would be 0, this would be 0, right? If we're talking about in terms of redox, that means zinc goes from 0 to +2. Is zinc being oxidized or reduced? That one's being oxidized, right? And hydrogen is going from +1 to 0. So that one would be reduced. Don't worry if you have no idea what I'm talking about. We're going to do a whole lesson on this, but that's just a little refresher of some of the redox stuff from Chem 1. Oxidation means you lose electrons. So going from 0 to +2 means you lost 2 electrons. And 2 hydrogens that are +1 going to 0 means they gain electrons, so they're being reduced. So just a little preview there. All right, a couple more things. talking about physical changes, different ways to write the equations for physical changes. Dissolution of soluble ionic salts. This would be like the balanced molecular equation here. All you have to do is write it as solid going to AQ. That's pretty easy. But if we want the net ionic, we actually have to separate the AQ. So for here, anything that's soluble, this would be showing the dissolution process where it's dissolving in water. You have to break the AQ, of course, up into its ions just like you would in any ionic, complete ionic or net ionic equation. So that would be for doing soluble ionic salts, dissolution. The dissolution of molecular solids. And as stated before on the naming slide, those ones are all going to be nonmetals. They do not form ions, they stay together. So you would not separate them. Doesn't break apart. So for instance, this is sugar, C12H22O11, what we put in our coffee and bake with, regular table sugar. So if we were we know that it dissolves in water, right? Everybody puts it in stuff. So we're writing out the regular equation to be solid to aqueous because it does dissolve. It has lots of OH groups, so it does bond well with water and the hydrogen bonding of water. But that is also the net ionic equation because it doesn't separate. It just stays together. So anything molecular where you know they're all nonmetals, remember the nonmetals are to the right of the staircase, and don't forget hydrogen. Hydrogen's a nonmetal. Okay, so that would be how you would recognize the molecular solids. Last but not least, phase changes can always be written in equation form. We already kind of talked about that, but let's take a look again at phase changes. Like the melting of sugar. People melt sugar all the time, so you go from solid to liquid. The only difference here, once again, nothing separates because it's molecular, so solid to liquid, that's how you would write the phase change. Okay? And the other example I gave you here is like the deposition of iodine. Deposition goes from gas to solid. Put the picture up here to show you iodine is this purpley pink gas. And actually in this first diagram, it's showing you it's subliming first, going to gas. Then it's depositing on here because there's ice in the test tube, so it's cooling it down. And it forms these like shiny silver crystals. So you just do gas to solid, very simple, kind of what we did in the other 4 notes so far. So 3 physical changes can be represented by equations: dissolution, dissolution of molecular, so dissolution of ionic, dissolution of molecular, and phase changes. So let's try a few real quick, see what we get.
What defines an ionic salt?
Metal, non-metal, or polyatomic?
Okay, so anything like precipitation.
Well, that would be a metal, but you'd also need a non-metal or a polyatomic ion. Okay, so let's take a look here. It says dissolution of potassium phosphate. You should recognize, yes, potassium is a metal, phosphate's a polyatomic, so this is going to be a dissolution of an ionic salt. If you looked at your solubility rules, you also would know that because it has potassium, alkaline metal is always soluble. This one would definitely dissolve. Snowflakes forming water vapor, that's just a what? Phase change. So that one's not too bad, that's pretty easy. And then the dissolution of ascorbic acid, and better known as vitamin C, that is what type? That's a molecular one. So do you have to separate it?
No.
And we see that it's molecular because it has all nonmetals in it: carbon, hydrogen, oxygen. All right, so the only one that you really had to do extra on would be A, because you have to separate the ions for the net ionic. And some people, you can take a look here, see how you did.